So, thus our goal is to work with this metric dt squared minus a squared of t multiplied by dr squared 1 minus k times r squared plus r squared d omega squared for the three cases of k equal to 1, 0, or minus 1. And our goal is to fix this factor from Einstein equations of motion. Well, it is straightforward to calculate from this metric the components of the Christoffel symbols. The non-zero components of the Christoffel symbols are as follows. It's a times a dot. A is a function of time only. It is not a function of spatial coordinates. That is due to the fact that we have spatially homogeneous situation here. So dot means it's differential with respect to time. A dot 1 minus k r squared gamma 0 2 2 is equal to r squared times a dot, and gamma 0 3 3 is equal to r squared sine squared theta times a dot, and gamma 1 0 1 is equal to a dot over a, and gamma 1 1 1 is equal to kappa times r 1 minus k 1 minus k r squared. Gamma 1 2 2 is equal to minus r times 1 minus k r squared, and gamma 1 3 3 is equal to minus r 1 minus k r squared times sine squared of theta, and gamma 2 0 2 is equal to a dot over a. Gamma 2 1 2 is 1 over r, and gamma 2 3 3 is equal to minus sine theta times cosine theta, and gamma 3 0 3 is a dot over a, and gamma 3 1 3 1 over r, and gamma 3 2 3 is equal to cotangents of theta. These are non-zero components of Christoffel symbols gamma, mu, nu, alpha for this metric tensor G mu nu. And the other non-zero components of the Christoffel symbol can be obtained from the symmetry properties of this tensor. And otherwise, if they do not follow, if other components do not follow from this by the symmetry properties of the Christoffel symbol, they are zero. We have written for you the the components of the Christoffel symbols for this metric. Now we're going to write the components of the Ricci tensor for this metric. The Ricci tensor components for this metric are like this: a double dot, second differential over time of a. R11 is a times a double dot plus 2a dot squared plus 2k over 1 minus k r squared. R22 is equal to r squared a double dot plus 2a dot squared plus 2k. R33 is equal to r squared sine squared theta a times a double dot plus 2a dot squared plus 2k. And then Ricci scalar following from this Riemann tensor and this metric is minus 6 a times a double dot plus a dot squared plus k over a squared. To find the behavior of a of time, to find this function from Einstein equations, we have to specify the energy momentum tensor. The energy momentum tensor, suitable for the situation that we are discussing, was already presented before. So it has this form of this perfect fluid. So it's rho of t times u mu u nu plus p of t times u mu u nu minus g mu nu, where g mu nu is a metric tensor written here. And the only peculiarity of this tensor follows from the spatial homogeneity. Because of that, we assume that rho and p are functions of time only, but not of spatial coordinates. In fact, in the comoving frame, in the free-falling matter in this metric has the following four-velocity vector, 1, 0, 0, 0. And as a result, this form of the energy momentum tensor has the following matrix. It is diagonal matrix of the form rho of t, p minus p of t, minus p of t, minus p of t. So this form of the energy momentum tensor for the matter is in perfect agreement with the spatial homogeneity. So first of all, we have rotational symmetry in space, and so all directions in space are equivalent, and all the components of this energy momentum tensor depend only on time. So we're going to use this energy momentum. Well, to move further, we will specify the components with both lower indices. T00, 0, as follows from here, is equivalent to rho. T11, again as follows from that, is pa squared over 1 minus k times r squared. T22 is equal to p r squared a squared. T33 is equal to p r squared a squared times sine squared of theta. So we're going to use this formulas, this expression, and the expression for the Ricci tensor, and the expression for the energy momentum tensor, plug them into Einstein equations, and look for the solutions which follow from the Einstein equations. So we are going to solve Einstein equation, r mu nu minus 1/2 g mu nu r equal to 8 pi kappa t mu nu. And we so far have specified this tensor, this tensor, this tensor, and this tensor. Now we're going to plug them into this equation and find the equation for unknowns, a of t, rho of t, and p of t. Well, we have to specify the relation between these two, which is called equation of state. So the equations that we obtain are as follows. It's 3a dot squared plus k equal to 8 pi kappa rho a squared. This is 0, 0 component of this equation. And 2a dot dot plus a dot squared plus k equal to minus 8 pi kappa p a squared. This is 1, 1 component of this equation. Actually, 2, 2 and 3, 3 components of this equation give the same due to spatial homogeneity, as it should be. And the other component of diagonal components of this equation give trivial relation that 0 equals to 0. Nothing else. And one more thing. We have also the condition of energy momentum conservation. It's 0. These are 4 equations. For nu equal to 0, we obtain the following equation: rho dot plus 3 p plus rho a dot over a equals to 0. And this equation is not independent from these two. It follows from these two equations. Actually, these equations are referred to as Friedmann equations. So this equation follows from this, and the equations for nu running from 1 to 3 give trivial relation, nothing non-trivial. Now, to solve these equations, these two or this, they are not independent again, we have to specify equation of state. The standard equation of state in cosmology is P equal to some parameter omega times rho, where omega is constant. Omega is constant. So we have already encountered several cases. First of all, for omega equals to 0, we have dust. That the pressure is 0. We have only rho. This is the case of dust. And in cosmology, it describes galactic matter spread over the universe. And the other option which is encountered in cosmology is omega equals to 1/3. For omega equals to 1/3, we obtain the energy momentum tensor, which is traceless, as one can check straightforwardly. And this corresponds to, this is called radiation. So this is dust, this is radiation. Why it is radiation? Because this case we encounter in Maxwell's theory, and that is one of the reasons why it is called radiation. Now one can look at this equation for these two options. First of all, for the case when W equals to 0, as a consequence of this equation, we obtain that rho, we already encountered this equation, in fact, rho times a cube is equal to constant, which just tells us that if the volume of spatial sections behaves like a cube, if the volume behaves like a cube, so it either expands or shrinks, hence the density behaves like 1 over a cube, the density of the dust, as it should be. For the case when W equals to, omega equals to 1/3, from this equation, we immediately obtain that rho times a to the 4th power is constant. Why is it so for the radiation? It is easy to understand, because for the radiation, again, for P equals 1/3 of rho, we obtain this situation. Why is it so for the radiation can be also understood, because the density of radiation also behaves like this if universe expands or shrinks according to this law. But at the same time, the wavelengths of radiation behaves like this. So this is a wavelength. The wavelength is scaling. The wavelength is scaling as a, so it increases. The frequency hence decreases, and as a result, the energy of radiation decreases according to this law. So the total energy density for the radiation hence is a product of this times this, and as a result, we obtain that rho behaves like 1 over a to the 4th power for the radiation. That is the reason we have this law for the radiation. So these two types of behavior for these two types of matter can be explained on general grounds.